Our next speaker is Camillo Brena, and he will tell us about regularity for stationary variable.
So thank you very much. I want to introduce the concept of varifold. And in order to do so, I just need one preliminary notion, and it's the one of Hausdorff measure. So let me define the Hausdorff measure HM as the m-dimensional Hausdorff measure. And I don't want to give you the definition that is a bit cumbersome, but let me just give you some intuition. So first, I think it should be the right tool to think when measuring m-dimensional subsets of a space. And then let me go through a couple of examples. So if, for example, you take H1 is the length of a curve, H2 is the surface area, H3 is the volume, and so on and so forth. But most important and more general, if you have a submanifold of the Euclidean space, then the Hausdorff measure on that submanifold is equal to the volume measure, so something that it's maybe it's more familiar. And actually, this is only the only case in which I'm going to use this measure. So I think it should explain what I'm going to use in what follows. Okay, let me just fix the setting. I'm going to work in Rn, this fix the Euclidean space, and take a dimension m that is strictly smaller than n. Okay, before giving the definition of varifold, a brief historical note. So first, Young introduced this concept as a generalized surface. And with the definition, we see that this makes sense because they are a way to generalize the notion of submanifold. But then Almgren called them varifolds. And the fact is that Almgren wanted to have an extension of the concept of submanifold that was done in the language of measure theory, but it was suitable for variational calculus. And I wanted to see this because this is maybe one of the explanations of the name varifold. So variational calculus and manifolds put together are varifolds. That is something that I was asking to myself some time ago. Okay, so let me give the definition. And disclaimer, I'm not really defining varifolds, but I'm going to define integer rectifiable varifolds. But today, I'll only consider this kind of varifold, so just let me take their short name and drop the integer rectifiable part in their name. And actually, what I'm going to tell you now is not the most standard definition, but it's easy to see that it's really equivalent to what you find in most places. Okay, so let me say that a varifold is a measure on the Euclidean space, and I want that measure to be called a varifold to be written in this way. So you want to have a sequence of submanifolds of the Euclidean space and take some subsets of your submanifolds, and you want your measure to be the sum of the Hausdorff measure restricted to these subsets of the submanifolds. And so as far as this slide, everything that is written here has been explained in the previous slide, because the only measure that we're considering is the Hausdorff measure restricted to a piece of a submanifold. Of course, when I'm writing this restriction, it means that I'm taking the measure and then intersecting every set that I feed to this measure with this subset B. Of course, probably you don't want to deal with measures that are always infinite, so let me ask something that shouldn't sound much restrictive. So let's say that this measure, I want this to be finite on bounded sets. Okay, maybe just for those of you who are more familiar with measure theory, you can see a varifold as a pair, R theta, where R is a m-rectifiable set, and theta is a density that has values in the set of positive integers. And you write, in that case, the varifold measure in this way. So the varifold measure is the Hausdorff measure restricted to the rectifiable set, weighted by your weight theta, that is a density that values in the integer values. Of course, once you have this representation of the measure, you get your set R and theta, and the other way around. So really, it's a matter of taste. Which one do you want to consider?
When you speak of submanifold or regular,
yes, you C1. Let's say C1. Okay, so this talk is about the regularity of these manifolds. Maybe general varifolds do not exhibit so much regularity, but let me add an assumption that will force some regularity in this topic. So let me define stationary varifolds. So to begin with, this is the definition of stationarity. This is very classical, and this definition is up to now is for submanifolds, and so it should be maybe most of you are familiar with it. So, but let me read the slide nevertheless. So you take a smooth and compactly supported vector field, and then you take its flow. And taking its flow means that you solve the ODE. So you start from a point and you evolve it along the line, along a curve. And this curve has tangent vector given by the test vector field that you are taking. And then you want to test the stationarity for a submanifold. And with stationarity, I implicitly means that I'm considering the area functional. So your submanifold is stationary if for every test vector field, when you take this variation, this is 0. So here you have your submanifold, you are flowing it along the flow. So you are simply moving it along your flow phi t. And then you are taking the variation of the volume, that is the area. And of course, I want to have stationarity for varifolds, but I don't want maybe to be more precise into the details because I think that there is no point in this talk to be more precise. But let me just say that here you have a volume measure, so you want to replace it with a varifold measure. But what you want to think about is how to flow your varifold along the flow. And maybe the most natural way to do it is recall that the varifold measure is a sum of pieces of submanifold, and so flow each of them, and then you put everything back together. And so at least this should give a meaningful idea of what it means to be stationary for the area functional for a varifold. And okay, just to investigate regularity, let me tell you what it's meant with a regular point for the varifold. So take a varifold and the point is regular if in a neighborhood of that point, your varifold was induced by a submanifold of the Euclidean space. So of course, the definition of varifolds involved a sum, so it makes sense that it's a reasonable assumption that when you deal with regularity, you allow that you are taking the submanifold with a constant multiplicity, as it has to be an integer, for example, pi. But okay, so let me write it down precisely. So being regular, X is regular if in an open neighborhood of X, that is U, whenever you look to the varifold measure in this open set, then you obtain the Hausdorff measure restricted to the submanifold, to a submanifold. Of course, you to look is the open set U, and times a constant multiplicity that has to be a non-negative integer. Here, the catch I'm writing 0 because maybe I don't want to deal with points that are outside of the varifold, so let me just skip the part that just to avoid some more notation. But okay, the fact is that you really want to be either far from the support of the varifold, so you see nothing, or you see a submanifold. Of course, if you want to define singular point, take points that are not regular. And now, maybe for those of you who wonder whether this definition is meaningful or not, let me give this example. So you are in R3 and you take two planes that intersect transversally. And this induces a varifold, right? Because these planes are honest submanifolds, so you can take the H2 restricted to them and sum these measures. So we have a varifold, and it's easy to realize that this is also stationary. And okay, so if you take a point that is not in the intersection, then this is a regular point because the varifold is induced by one of the two planes, so it is a submanifold, and we have a lot of regularity. If you take a point that is in the intersection, so in this line, then you can prove that this is a singular point. So the aim of this slide is to see that there are, in general, many regular points, many singular points. And so the next question maybe is to ask whether we have some bounds and maybe how many singular points can we have from for this theory of stationary variables. And okay, here is the main theorem. So 50 years ago, almost 50 years ago, I would say. So take a stationary varifold in the Euclidean space. And then the assumption is that near a point X, your varifold is close enough to a very simple varifold, the one induced by an M-plane in an end. And here you have to be close to this with constant multiplicity 1. So I'm not allowing a weight. So this theorem does not give a conclusion if you are close to 2 times the varifold induced by a plane. I've been not precise telling you what do I mean by the varifold measure to be close enough to another varifold, but these are all measures, so I think that you can take your favorite topology and this will work. And also that there are some other notions that enforce this regularity, but maybe the meaningful ones will give the result. But this is not maybe the point. And then, of course, the claim of the theorem is that we got a regular point. And let me just give a corollary of this theorem, a very important corollary. And the corollary states that for a stationary varifold, the set of regular points is an open dense subset. The fact that regular points are open, of course, it's nothing important because they are by definition open. But what is the takeaway is that they are dense. And this claim has a kind of topological taste because I'm saying that regular points are dense, and indeed its proof has a topological flavor because you start from Euler theorem and use some bare category argument. This is not very hard, so that the big work stays here, but with some more epsilon work you get the corollary. That is maybe useful. And before going on, let me conclude this slide with a couple of remarks. So the first is that there is nothing wrong in regarding this theorem as an epsilon regularity theorem, because the assumption is that close to a point your varifold is close to a very nice model varifold, and the outcome is regularity of what we get. The second, I said it before. So I said it before that this constant multiplicity must be 1, but I want to stress it again. And so let me say that the fact that I'm not allowing to have a higher multiplicity on the model space to which you want to be close is not because it's not by mistake, but this is because if you allow higher multiplicity, then this theorem becomes false. And actually, so you see that in particular, its proof fails. And this fact is one of the reasons why, if you want to have sharper theorems sharper theorems starting from this, you get in trouble easily. And we are going to see this in the next slide. And finally, let me add this almost trivial comment, is that near a regular point, your varifold is induced by a submanifold, but your varifold is stationary. So this submanifold must be stationary itself, just take variations in that neighborhood. And so that was a minimal surface. And this was just to say that if you are a regular point, then you are much more non-regular because minimal surfaces enjoy very beautiful regularity theory. And okay, so let me wrap up the previous slide by saying that for a stationary varifolds, singular points have empty interior, and this is because regular points are dense. And okay, but what is true is that people expect that singular points have codimension 1. So this is something that is way, way stronger. And let me recall the picture of the two planes intersecting transversally. In that case, singular points were aligned and the varifold was two-dimensional. So in that case, this would have been sharp. So we cannot expect better, but still we do expect it. This is a very open. I think this is very far from the known. And but there is some literature, but for particular cases of, for example, if you look to stable to codimension 1 in particular cases. But last, let me consider this intermediate claim. So the fact that the varifold measure does not see singular points, so this should maybe sound natural. And this is considerably weaker than what we don't know from the second ballet, but this is slightly stronger than the topological statement that we already know. And with a bit of disappointment, I say that also this is very open, so still there is a huge gap between what we know from 50 years ago and what is expected to be true. And okay, let me conclude this talk with this last couple of slides. I want to switch from varifolds to currents without maybe defining currents, but let me tell you how one can think about these objects. So let me recall that I tell you that you can think about the varifold measure as the sum of Hausdorff measure restricted to a bunch of Borel subset of submanifolds. These submanifolds may be oriented, but doing this procedure, I completely forgot about the orientation. This is because varifolds definition does not require anything about orientation. But you can keep track of the orientation in a sense. And if you do like this, you obtain some sort of oriented varifold. This is actually defined as a current. Again, you should call integral currents, but let me say currents. Now, I don't want them to be precise, but currents are some sorts of stronger definition that involve a kind of orientation. But what you can do when you have an orientation is to define a sort of a boundary. And so I think that it's useful to think about Stokes' theorem for the integration on oriented manifolds. This tells you that if you have an oriented manifold, then you can integrate the differential of a differential form and look to the boundary of your manifold. And so in this way, we have a formula involving a boundary. If you take this, if you force this as a definition of the boundary of a current, you get the definition of the boundary of a current. So this is to say that in this context, you have a boundary. Of course, you have boundaries, so you can consider the class of currents sharing the same boundary, and so you go towards the framing plateaus problem. And so the only key takeaway is that when you speak about currents, there are area minimizing currents, so which are the currents that minimize the area among the class of currents with the same boundary. You expect them to be more beautiful because these are minima of a functional, not only stationary points, and indeed they enjoy a better regularity theory, but I don't want to conclude with regularity theory for currents, but with another principle. And so this is the last slide. And I want to start with the following principle that is a remark that maybe is found in the paper between the lines of Algren and the one of the remake by Dell'Ellis and Spadaro about Algren's regularity theory, that states that for area minimizing currents, the issues of regularity and unique continuation are two objects that are intimately related. So they are some sort of relative one to the other. Without entering into details what it means unique continuation for this kind of currents, let me just give you the example for function. So for function, enjoying the unique continuation principle means that if you have a function and the function and all its derivatives vanish at a point, then your function must vanish. This is also unique continuation, and because analytic continuation, because analytic function, of course, enjoy this principle just because you have a sort of polynomial, and then you can kill all the terms in this polynomial. And okay, so the result that I want to use to conclude this talk is that if you have an area minimizing current, then you have a sort of unique continuation principle for that current. And so the assumption is that if your current has infinite order of contact with a plane, with an n-plane, I don't want to be precise about what it means to have infinite order of contact, but it should be the replacement of this condition. So if it was a graph that every derivative vanished, then the claim is that you want to have this right-hand side, and so that the current is equal to the plane in a neighborhood of that point. And so that was everything that I wanted to say. So. Questions?
Ask a question. It's a highly technical question because I simply don't remember. So in this context of like stationary varifolds, do you have bounds and Green's functions?
I don't know.
I don't know. Okay.
I don't know. Yeah, can
you give an example of a varifold which is not stationary?
Well, I think that every kind of varifold that you want to think it probably won't be stationary. Just take any kind of submanifold that is to take a sphere, for example. I mean, stationary is. So it's you can take a surface and ask whether this is a minimal or
not. When you prove the density of the set of regular points, is that inside like the big ambient space or inside like the support of the
if you have in the support of the measure, you can't. If you take the definition of that points outside the support of are regular, then you get that for free, right? So it's just a matter of notation. I tricked you just saying that points outside the support are regular just because I wanted to be a bit lazy, but I think that if you think them up as being regular, and I think it's reasonable to do that, then it's okay.